Hey everyone, my name is Shiwen. I'm very excited to share a new collaborative filtering models we developed at Apple. This work is done with Charlie and Guillermo. To begin with, let's look at the recommendation problem and traditional collaborative filtering methods developed for this problem. The recommendation problem starts with collecting users' historical interactions. For example, in e-commerce, users' view and purchase history, and even explicit ratings on products are such interactions. This domain can be extended beyond the e-commerce applications. Users' historical interactions can be summarized in a user-atom interaction matrix. Each entry in this matrix represents one interaction between corresponding user and atom. In this work, we consider the most basic scenario where the interactions are binary. In this setting, the interaction matrix becomes a matrix with positive entries on actual interactions and negative entries on others. Given this binary matrix, collaborative filtering models decompose the matrix into a user and atom matrix, possibly low-dimensional. The user and atom matrix contain user and atom embeddings. Atoms with embedding vectors that are more closer to user embedding vectors are recommended to those users. The well-known Bayesian personalized ranking model relaxed the original assumption by proposing non-interacted atoms are more likely to be less favorable than interacted ones, not necessarily disliked by users completely. With this assumption, the user-atom interaction matrix can be converted to a three-way tensor, with the first axis represent users and the other two represent atoms. Slices at the first user axis are atom pairwise comparison matrices, and that pairwise comparison matrix suggests which atoms is more favorable for a particular user. The pairwise comparison matrices are incomplete, with missing entries suggesting no concrete preferences are available between those atoms. Rendell et al. Parameterized the binary three-way tensor as a Bernoulli distribution. The underlying parameters x form another three-way tensor with the same shape, but having entries representing the natural parameters of the individual Bernoulli distributions. Parameter estimations can be done by finding the right parsimonious representation of the underlying parameter. Bayesian personalized ranking model assumes x, u, i, j for user u, atom I, and j can be represented by this equation. This is the difference of the preference strengths of user u on atom I and j, respectively. The parameterization has a long history in investigating pairwise comparison matrices and can be dated back at least to 1986. The preference strength xui can be further parameterized as a dot product between a user embedding vector and atom embedding vector. With this parameterization, the original parameter tensor X can be fully determined by the user and atom matrices formed by the embedding vectors. Similar parameter underlying similarly to similar to parameters underlying to all pairwise comparison matrices, the parameter tensor X has a property. For any user U, the first order slice of X, XU, is an anti-symmetric matrix. The previous two equations can be rewritten in a matrix form. In this example, the Xz is one entry in the user embedding vector, and the eta superscript h is one row in the atom matrix. The subscript h indices factors. It runs from 1 to k, where k is the dimension of the embedding space. The one vector in the equation represents an all-one vector with the length of m, the total number of atoms in the model. In fact, the all-one vector can be replaced by any other vector, and the anti-symmetric property still holds. In our work, we replace the O1 vector by tau. A vector takes positive values. The rationale will become clear in next slides. As a consequence, a new atom embedding matrix T is introduced. We can rewrite the original Bayesian personalized ranking model in first equation. The relative preference between atom I and J is formed by the contribution from k terms. Each one corresponds to one factor in the embedding space. The term can be viewed as the difference of preference strength between atom I and J and a specific factor. The introduction of the third atom, tau, extends the traditional dot product to inner product, and that's the reason why we require the value of tau to be positive. Now, when evaluating the relative preference between atom I and J, the preference strength of I becomes dependent on atom J via the tau vector of J. Same holds for preference strength of atom J. The resulting consequences are preference strengths become relative instead of absolute. The preference strength manifests at the time of making pairwise comparisons. The implication is profound. In traditional covariance filtering models, if atom I is more preferable than atom J and J is more preferable than O, then atom I must be more preferable than O. This is a known property called transitivity. And in our model set, we relax the property, allow it to be inferred from data itself. This figure shows the underlying value of hyperparameters during the application of a stochastic gradient descent algorithm developed for our model. The figure shows multiple trajectories of the optimization curve under different hyperparameters such as learning rate, the weight for L1 regularizations, and so on. Our stochastic gradient descent algorithm behaves quite well in the natural real-world dataset. We compare our new model with traditional collaborative filtering models and show that our model set is able to produce the most consistent preference estimation between atom pairs. When using the pairwise preference as a means to perform recommendations, SET outperformed a lot of alternative models as well. The final slide shows a few examples in which SET produced the pairwise preference that is consistent with real ratings, while other model fails. For more details, you are encouraged to check out our paper. Our code is released in the Python library shown above. Thanks for your attention.